All right, folks, today, last lesson of the chapter. Aren't you excited? Maybe. Interpreting inverse relations graphically. Actually, I think I sort of talked about this in the last lesson, but today we get it down to it a little more specifically of how we do these graphically. And now, I don't know if this is funny. Due to its graphic nature, the following has been rated restricted. See, because it's graphically, so it's its graphic nature. Best I could do on a Tuesday. All right. Investigation. Find the inverse function. One of the things we learned on Friday was that f with little negative 1 doesn't mean exponent. I'm not sure it was a great choice by mathematicians, actually. Mathematicians made a lot of great choices, but putting a little negative 1 up there that looks like an exponent, I'm not sure that was a beautiful choice. But that's what we mean. When we say f negative 1, we mean inverse. We mean do the opposite. Undo what you did. And we talked about adding becomes subtracting and multiplying becomes dividing, always undoing. But when you're given ordered pairs for a second, it looks more difficult, but it's way easier, way easier. If my function f takes negative 2 and turns it into negative 8, your inverse function has to do the opposite. It has to turn negative 8 into negative 2. So all you're doing is taking the point negative 2, negative 8, and flipping it over to become negative 8, negative 2. I don't know why it's flashing like that. I'll just leave it for a second. Maybe it's going to do a funny animation for us. Maybe that's what's happening. Then the next one, 0, negative 2. If my function f goes 0 to negative 2, your function's got to go negative 2 to 0. Oh, it's starting to do it now, okay? See, just flips its roles around to negative 2, 0. If my function does 3 to 4, yours does 4 to 3. If my function does 4 to 7, yours does 7 to 4. If you're expecting some other really difficult thing in the graphical interpretation, it might not be coming. That might be as difficult as it is with the points. And you don't have to do it with just points. You could do it with the whole graph just by doing this with the individual points. We'll see more of that a little later. That's it. If they give you a list of points, reverse x and y. Now, we did say that in the algebraic version of this. We said reverse x and y, or exchange x and y. But it's easier when it's just points. You just individually exchange the points. Is there any questions there? All right. That's pretty good. Now, there is something interesting that happens when you graph it, though. Here's the original points. I'm doing them in blue and red. You might want to do them light and dark, or do dots for the f and little x's for the f inverse. You want to be able to see the difference between the two. I'll get my first set of points up there. If I was graphing f, I get negative 2, negative 8, 0, negative 2, 3, 4, 4, 7. There's my function in blue. Again, you might want to go with dots for f if you don't have a separate color. If you've got a separate color, well, you can do what I'm doing and do it in 2 separate colors. Then I'm going to also graph the inverse function, these inverse points. Instead of negative 2, negative 8, I'm going to do negative 8, negative 2, which is over there. And then I'm going to do negative 2, 0, 4, 3, and 7, 4. At that point, it's not too exciting. You're like, yes, so what? But there is something interesting that happened going from the blue to the red, and it might be difficult for you to see what happens between the blue and the red until I put a diagonal line on there. And I'll do it on the board here. If you're looking at this as a video, just draw a diagonal line through the center. I'm going to put it on in a second, but I just want to put that up on the people in class there at the line y equals x. Do you see something interesting about the reds and the blues? It's a reflection. It's a different kind of reflection, and maybe now you see why we had to be so specific about reflections. It's, oh, I'm losing it there. It's a reflection in the line y equals x. Fascinating. Let me see if I can draw that line on there. I don't know if PowerPoint gives me straight line tools, so I may have to really play around here. Pointer options, pen, and I'm going to actually use a ruler in class here and draw on that line y equals x. I don't know how good it's going to be. Not great, but not bad. Hopefully you do better on yours. A diagonal line right through y equals x. And now do you see the red and the blue have just been flipped over that line? That's hard to understand until I explain one more thing. What's really happening, I'm taking x and y, and I'm exchanging those, x and y. And if I rotated this like that, that's what would make those points do that. It's sort of weird. Question. What's that? Oh, yes, thank you. You're welcome. Okay, well, for us in grade 11, it's really important, we know, to take the x's and y's and exchange them. Having a perfect understanding of this reflection in the line y equals x, I'm not sure we need that just yet. I mean, it's nice to see it, but that's not really the big point of the lesson. The big point is just exchange the x and y's. I don't want to get sidetracked from that major point, because I said that was the major thing in the lesson, and I stick to that. Lost my controller. The next slide may just do that actively in the PowerPoint. How are the graphs and f inverse related? They're reflected in the line y equals x, and the PowerPoint draws a really nice line there for you on your next slide and really puts the arrows in there. Look at, maybe me explaining it wasn't good enough, but those little arrows, see? They've been reflected in the line y equals x. A little bit mysterious how that plays out. Why does this relationship make sense? Okay, my best explanation is because if you take the axis of x and the axis of y, and you exchange the two of those, that's going to spin this whole thing diagonally, and all the points spin diagonally. Phrased another way, for the inverse function, the x and y coordinates are exchanged. So the domain becomes the range, and the range becomes the domain. Is that already written on yours? That slide's fairly complete, isn't it? Yes. So this line I want you to get down. The graph of f inverse is the reflection of the graph of f in the line y equals x. I do want you to have that down, but again, I'm not setting you up for a major question on that on the test. I just mention it. Really, this exchanging the x and y's is the important part of the lesson. Do you have any questions? Do you need more time there? Is it okay? Yeah. So, determining if the inverse is a function. Recall that a function is a relation for which every x value has one corresponding y value. That went really well on the quiz. Most people knew that. We can check if the graph of a relation is a function using the vertical line test. We've been using that before. Is there a way we can use, it's a test we can use on the graph of a function, determine if the inverse will be a function? And I mentioned this in another lesson. Yeah, you can. You can look at it and use the horizontal line test to find out if the inverse will be a function. Somebody else says, can't I just find the inverse and then do the vertical line test on that? That's doing the same thing. So yeah, you could keep using the vertical line test. But I mentioned the horizontal line test because it does come up later on. If any horizontal line passes through more than one point in the graph, then the inverse is not a function. So there is a vertical and a horizontal line test. Vertical line test tests if something's a function. Horizontal line test tests if the inverse will end up being a function. Do you have to write any of that? No, it's just all there for you. Did you have to write vertical line test? You did have to write vertical line. Sorry, you did have to write vertical and horizontal line test. Carter, question?
Do you mean like all parabolas would be like, their inverses wouldn't be like?
All parabolas, their inverses won't be a function. It's the perfect one to talk about because it doesn't survive. And here's the reason why. If I tell you the x value of a parabola, you can find the y value. You know exactly what it is. If I tell you the x value is 4, you know the y value is 16. If I tell you the x value is 10, you know the y value is 100. The reverse doesn't work though. If I tell you the y value of a parabola is 100, you don't know which x value you're talking about. It fails the horizontal line test. And so that's why its inverse won't be a function. That's why we end up with plus or minus square root. There's two different answers there. So we're just stepping just slightly outside of functions, which is the name of the course, but we're sort of forced into it by finding the inverse of some of the functions we have, we find out their inverses aren't functions. We sort of stop there and go, "Eey, oh, scary." It's not that scary. When we know what it is, a sideways parabola. It's not that scary. But it does fail the vertical line test after we do it. Yeah. Why does the horizontal line test make sense? The x and y values have been exchanged, so the test is exchanged. That is, if we were doing a vertical line test before, if we want to test the inverse, we're doing the horizontal line test. Functions that do this, that pass the vertical and the horizontal line test, are very friendly functions. They're a special kind of functions called one-to-one. Usually written as one-to-one. Yeah, just like that. Yeah. Why is name appropriate? Every x value has one y value. Every y value has one x value. So it's one-to-one. Every x value matches up exactly with one y value. Again, there's lots of real life stuff that isn't one-to-one. There's lots of real life stuff that isn't a function. We just have to label them so we know which kind of functions we're talking about. Each y value has one corresponding x value. Also, each x value has one corresponding y value. Is that just a list of information? Copied nothing there, did you? Oh, that's good. An example. Okay, let's get it into real terms of stuff that we can do. Sketch the graph of x squared plus 2. What does y equals x squared plus 2 look like? It's just a parabola, but moved up 2. So there it is. I hope, and I think when I mark the quizzes, any one-step things like this, most people had no trouble with the individual steps. That's some minor problems. It was when all the steps were put together that things got a little crazy. Yeah? And something to work on. When I give the quizzes back, you're like, okay, let's go over this so we can be ready for the test. Yeah? Is this a function? Yes. Old friend. Passes the vertical line test. Will the inverse be a function? Without doing any other work, can I tell by looking at it? Carter already answered that with his great question last, and say, no, this fails the horizontal line test. So I know without doing any work that the inverse will not be a function because it fails the horizontal line test. Do you have to use the horizontal line test? No. You could go and find the inverse and look at it and see if it passes the vertical line test. Oops, I jumped on you there. So I'm not saying the horizontal line test is unnecessary. It's just a shortcut that you don't necessarily have to use. Just looking at my sheets to see where I'm at there. So now I'm going to go ahead and do it the other way and say, can I find this inverse? And once I find the inverse, I'll put the vertical line test on it and see if my prediction's right. The horizontal line test says you're going to find out it's not a function, but I'll do it. I'll go through the steps. Find inverse. All right, this was not on the quiz, right? This is separate. You look over your quiz later, you look at my solutions and go, oh, okay, I'm a little more ready for all that stuff now, but inverses wasn't on there, so you're going to have to pay special attention to that in the review. What was the first step? Does anyone remember this now, after all that studying for the quiz? What's the first step of finding the inverse of a function? Write f at x as y, because that'll make the algebra easier. I haven't done any inverse there yet. The actual step of finding inverse means exchange x and y. Actually take the x and make it y, take the y and makes it x. So it is a new y and x. It's just exchanging the roles. So a new equation. The inverse will have equation x equals y squared plus 2, which actually is legitimate. That's the legitimate equation for the inverse, except we're used to seeing it as y equals. So then our job is to solve for y equals. So I bring the 2 over. Here in this particular version of the algebra, I wanted to solve on the left. So I exchanged the two sides of the equation. Totally allowed. It's not an algebraic move maybe you've seen a lot of, but it makes things a little bit easier to go, well, if x minus 2 is y squared, then y squared is x minus 2. I'm just writing that in the order that I prefer. Now, I nominate this step as the one most likely that I will take the most half marks off on the upcoming test. So maybe you'd like to red highlight this and go, well, not me. I may lose marks on a lot of things, but not on this step. Let me ask you, what's the opposite? What's the inverse of squaring? Plus minus square root. It's our fault. I apologize. The Pythagorean theorem led you to believe that you only had to do square root, and that's not true in general. The inverse of squaring is plus minus square root. And then the last step of finding the inverse is to write it using the inverse function notation. So the f inverse is plus or minus square root x minus 2. Now I'm in position to graph this thing and see if it actually does fail the vertical line test. What does the square root function look like? I challenge you now. This late in the chapter should be like, in my brain, I'm starting to remember what these things look like. And the square root's half a sideways parabola. We did that investigation, which I'm going to get back to you tomorrow. Anyone who hasn't handed the investigation in by, well, after this, I'm going to go talk to people with quizzes and investigations and get those things taken care of. So, half a sideways parabola, but not just half a sideways parabola, it's got a minus 2 inside. So right 2. So there's the positive side of this, but the plus or minus says also do the vertical reflection, and there's the other side of it. There's the inverse function, and you see it fails the vertical line test? But we could have predicted that. We could have predicted that by saying, well, if this one fails the horizontal, this one's going to fail the vertical. But you could go through all the steps and just find the inverse function. And then I'll graph the line y equals x, just so you can see that weird reflection thing going on there. Take a look at that. Can you see that it's a mirror image along y equals x? It's been flipped over there. Strange. That's not how I really think about it. I think of it as if somebody reached up and grabbed the y-axis with one hand, grabbed the x-axis with the other hand, and physically exchange them, that would mean spinning the axis diagonally, and that's what happens here, is y and x have been exchanged. Literally, y and x have been exchanged, and that's why it does this rotation thing on a 45. So, the only last question of this section. Oh, you're having trouble seeing the f inverse in there. Let me just write that in there. It doesn't come through once in a while on the PowerPoint very well. So let me just switch colors here and get a color that you can see. That was supposed to be f inverse. Or is that already on yours? Oh, we're on slide 9 now. Yeah, so it's already on there. Okay. Now, so then somebody says, well, I don't like that. I don't want the inverse to not be a function. And you might not care about that right now. But if I didn't want the inverse to a function, the next slide says, can I restrict the domain? Can I make a version of y equals x squared plus 2 where I can take the inverse and end up with a function? And the answer is yes. If I only use the right-hand branch of this thing, then when I do an inverse, I'll only have one branch. Seems like a weird move. It is a very weird move at this point. So it says, can I restrict the domain so that f and f are inverse? Yes. Restrict f at x to only positive values of x. Oh, you need more time there, do you? Copy that down. And then I'll show you what I mean. I'm only going to use the right-hand branch of the first function, and if I only use the right-hand branch, then I only have to use the upper branch of the second one. And then everybody's a function, and we get to go home happy. Does that matter? Not yet. But when we want to have a function, we're going to have to restrict the domain and tell people, don't use x squared plus 2 the way it is. If you want to take the inverse, only use the right-hand branch. Don't use both branches. Okay? I'm trying to give enough time here. Do you need more time on this slide? Okay. I think the next one's the last slide. Am I correct? I'm on slide 10 of 11. Well, that's good, because I got to wrap up and go copy your review for you. Where did I put it? Oh, I found it. And talk all about the rest of the week. PowerPoint says restrict f at x to only positive value of x or only negative values of x. It is a choice. Most times we'll go with positive. Why would you use the negative unless you were forced to? So if you want to make this so that the inverse was a function, only use the right-hand branch. And I'll come back. You can tell me in a second to come back. I just want you to show you what I mean in the last slide here. With the domain restricted, I get only the right-hand branch. There's a nice one-to-one function. By only using the right-hand branch, when I do the inverse, I get that thing. Now everybody's a function and we get to go home happy. We go no farther with inverses there. We'll pick that discussion up in advanced functions and go, are we just allowed to restrict domains? And the answer is yes. You can always restrict the domain of a function if you want to. And here I said, okay, I'm only going to use x values greater than 0. So for my inverse, I only got y values greater than 0. And so now it passes, both of them pass the vertical and horizontal line tests.